So, welcome, and today we would be learning about classification with a multilayer perceptron. And while we have done down our basic introductory lectures on what a multilayer perceptron is and then how to use it for classification. So, here the objective is that building up on top of what we had done in the previous class of using down just a set of features extracted from the images, and then we were feeding it through a neural network, and this neural network just had inputs connected directly to the classification output. So, you had 9 features which were going down on the input side of the neural network, and it was just connected down to one hot vector of 10 cross 1 dimension, and that was basically because it had just 10 classes over there to classify. So, any one of these classes is going to be 1 based on which particular class is being shown over there. Now, one thing to remember clearly over there was that that was a very simple perceptron model which did not have any number of hidden layers. But then when we were doing with multilayer perceptron, we did realize that you can add down more number of hidden layers, and that would subsequently introduce a lot of nonlinearity over there, and this nonlinearity will be some sort of a hierarchical nonlinearity going down over there, and that would help you in creating much better separation margins by learning much better kind of features as well. So, here today what we will do is write down such a network which will have multiple hidden layers over there and see how it gets trained. So, building up on top of the scratchpad which we had used for creating a simple perceptron, we will be starting for that. So, let us get into how this code particularly works over here. So, the first part, so this is on classification with a multilayer perceptron, and this is still for your CFAR 10 dataset itself. Now, in this first part we just have the initial header, and there is not much to redefine around this header as well, because we are just going to keep this as the same header over there. So, let us just run and get down our initial files into the environment. Now, once that is done, the next part is that you already have your features which were saved down from lecture 3 exercises, where we had basically learned how to collect these features. And so, we run them, and these features come down to me. Now, once I have loaded down all of my features on and my labels both for the training and the testing over there, the next part comes down to defining this network. Now, you clearly remember that in the last case what we had was that so this class was called as a perceptron in that case, and here we are calling it as MLP. So, MLP stands for multilayer perceptron, and then multilayer concept is which comes down that you have multiple number of layers given down over there. So, multiple number of layers in terms of multiple hidden layers present down. So, the first part is basically an initialization module. So, in this initialization module, what you do is that you are going to define how many number of layers over there. So, we have 2 layers and both of them are linearly connected. So, the first one is which connects down n number of channels to 6. So, n channels over here is the total number of features which you are giving down to this network. So, that is basically 9 for our case, but it can be any variable number. So, this is a 9 to 6 mapping. So, this 6 number of neurons is the number of neurons present down in your first hidden layer. Now, from that first hidden layer it connects down to 10 which are my output mapping, and this 10 maps down to my total number of classes in the output. Okay. Now, once that is done, the next part is left with that I need to define what is my forward pass of this algorithm. So, in order to define my forward pass of the algorithm, what I define is that whatever comes as in my input over there, that has to do the first pass through my L1, and L1 is a n dot linear, which is a mapping from n number of channels to 6 channels. Okay. Now, once that is done, my output is again stored at x. Now, that will have a nonlinearity, and the nonlinearity imposed over here is a ReLU kind of nonlinearity which we put down. So, this ReLU or rectified linear unit is something which is for any value less than 0, you will truncate all the values to 0, and for any value which is greater than 0, the value will remain as the same. So, this is basically some sort of a form in which it remains linear for positive values of x and becomes 0 for negative values of x. Okay. The next one is another feed forward which you do through the next linear layer, and then finally you put down softmax as your nonlinearity coming down from the output of it. Now, once that is done, the next part goes down in your so this is my network which gets defined over here. So, let us just define my network. Now comes down the data preparation stage over there. So, in data preparation, what we had done in last class was quite simple. So we defined two matrices, two sort of like two matrices which were 50,000 cross 10 and another was 10,000 cross 10, and this was just for your labels. So you remember clearly that we had labels in the range of 0 to 10, but then when training this network we needed to have a one hot vector, and that meant that it needs to have 10 number of rows corresponding to 10 number of columns corresponding to each single row, and any one of these items on these rows is going to be 1 based on which particular class it belongs to. So we start with the same way. So your train label becomes a 2D matrix of 50,000 cross 1, and your test labels also become a 2D matrix of 10,000 cross 1, and accordingly over here you do your reassignment. So just assign whichever value, whichever class is 1, you assign that value as 1 over here. Now once that part is done, the next part is to work and create down your convert your data set which is available as of now as a NumPy array to a torch tensor, and that's what we were doing it. So this part of the scratch is pretty much same as what we had done in the earlier class, and then the next one was to check down whether you have a GPU available and a CUDA support on your system or not. Now once that gets done, so we start by defining the training routine for our model. So within this training routine for the model, the idea was that you would have some sort of an iterator, and this is an epoch iterator. Now within the epoch iterator, there is a fancy sort of a function call over here for the time, in order to check out how many seconds, milliseconds it takes basically to execute each of them. So we remember from our last one that it was taking roughly about 1 second, and in total for 20 epochs it took down 27 seconds to execute. So from there, the rest of the concepts in terms of running laws, then creating a batch over there and using your train loader, that remains the same, and then if GPU is available, then to convert all of these to your CUDA tensor type, so that you have a memory transfer from your CPU RAMs onto your GPU RAM. That's also quite clearly done, and this is what we are just repeating from the earlier case. Next, before you start training, you need to always zero down your gradients. Once that is done, next is the feed forward routine, and that defines as output is equal to model of input, and model is basically the function which is my multilayer perceptron neural network. So given all of that, the next part is to use these output in order to get my predictions for each of these classes, and then from there find out my loss, which is defined according to this criteria. So the criteria function gets defined a bit later on. As of now we are just using it as a simple pointer called as criterion, and then you find out your batch wise losses, and finally comes down the point where you need to update your parameters. So here is where this happens. So if you clearly remember, you have multiple number of hidden layers over there, and there are multiple number of connections between each of these neurons in one layer to the neurons in the subsequent layer, and this is what is called as those free parameters or the weights, and these parameters are what get updated. So your update rule, which was given as W of k plus 1 is equal to W of k, where W of k is basically the weight of these connections within the neural network at the kth iteration, and minus eta times of del W of JW at that kth iteration. So we need to have our gradient of the data as well as the learning rate, and that is going to define down what is my update parameter over there. Now from this, once your parameters are updated, then you can actually look into your total epoch loss. So what we are doing over here is that you run down basically 50,000 training samples throughout one epoch and accumulate all the errors. So your epoch loss is basically average of that error, and that's where this part comes down, and then you can keep on basically creating an array where you are adding down all of those losses, and it becomes easier to plot down. Now here you have these printer statements which basically print down what is the total epoch loss which comes down while it's training down, so that you can see that it's convergent or not. So this is where your trainer module gets defined. So let's just run this part and get it prefetched as a function within your environment. Now once that's done, the next part is to actually get into your initialization and training. So the first part is we need this length of features, and this is what we know from our earlier experiences. You can as well look into the dimension, second dimension of the pickle file arrays and fetch it out as well. That's also pretty much possible. Now within your model, first thing is that since we have CUDA available, so we just defined it, typecasted it once again into CUDA, and then defined the criterion or the loss function as a MSE loss function, and then we set this one to train. Now let's and then we are training it again with just 20 epochs in order to look into how it starts to behave. Now we do see our losses coming down over there, and if you look down, so this is where the error is changing around on these points, and then that's changing down quite slowly. I won't say that it's pretty fast, but there is a decent amount of decrease which keeps on going down, and although sometimes it does even look to increase as well. So and then it's roughly taking down, it shows as 1 second, but there are a few more milliseconds as well. So yeah, you see that it do not take actually much more of a time as compared to the earlier one, because you still finished off your 20 epochs within 27 milliseconds, and this is how your training loss was falling down. So you can add down the extra module which we had in the earlier one in terms of accuracy, and you can see the accuracy growing as well. Now once that is done, the next part was to go with your train module and then look into its testing part. So over there what we do is we pull down, we run an iterator over the test data set, over the length of the test data set, and then feed forward each input through the model, which happens over here. You get down your outputs and then see if your predicted output matches down your exact output, and if it is so, then it is correct or not. And interestingly, what comes out is that since the training has not yet completed, so you get down a 0 accuracy, but you can keep on running this one for a longer period of time. So for the sake of time constraints, we are not running this for longer duration of time, but you can definitely try running this for a longer duration of time. Now there are a few interesting aspects which I would like to reiterate from our earlier understanding. So one of the major point is that if you look into most part of this code, then they are actually something which is quite modularly written down. So if I want to create a change in my model, say I would like to change down my nonlinearity, so I can just make a change over here or over here. If I want to add down a few models over there, so if I say I want to add down a few more linear number of channels, so I can just keep on adding down over there. So say like I just want to add down another layer, I can write it as nn dot linear. So I have 6 number of outputs from there. From that 6 number of outputs, I can again think of going down to say another 6 number of outputs over there. Okay, that's also pretty much possible. Then I can do nn dot linear from and so this will be self dot L3 is equal to nn dot linear of 6 to 10. Now once that is done over here, till this point I just had with the self dot L2, and what I can add is x is equal to self I can add another ReLU and get a nonlinearity imposed over there. Now once this part is solved over here, the next part is that I will have to again feed that through another part of the layer, and that becomes x equal to self dot L3 of x, and from here whatever comes down, that goes into my softmax, and then this will create down a new model. So we can just do a run on this one. Now once that is done, I can again do the subsequent runs over the next, and here comes my training module. So you see, increasing that, I just got a tad bit more increase. It came down to somewhere around 2 seconds, and so we just need to wait for few more moments till it gets over. So like to you it should be a much easier way, because within this library, although it looks like a lot of lines of codes, but most of these are modularly written. So if you want to make change onto your architecture, there is just one function over there which defines these architectures, and you will just have to make a shorter change. So by now it's complete. It took down about 32 seconds, and you can see that it had a bit of jagged behavior, and it was much slower in actually falling down. So the error did decrease to a much lower front as well, but then the rate at which it was decreasing also became slower. So it's not always necessary that just by increasing the number of neurons you will have a much better decrease over there. So I can even play around with the learning rate over here. Say I make down my learning rate as 1, and I can again set that one running. So I just need to execute only this part of it. Keep one thing in mind: if you are making some changes to a previous one, then you need to execute all the subsequent blocks so that it comes down. So this is on IPython notebook, so it gives you a much interactive way of solving it out and a much better way of learning. You can always copy all of these into a direct Python code and it will appear in the same modular way within your Python environment, and you can just execute that py file within whatever is your choice of environment. Most likely most of us would be making use of Anaconda Python in order to do that, and that becomes easier. So you see that when I changed it to a learning rate of 1, this is how it was falling down, and then that wasn't even a steady fall. So it became much more linearly falling down and much jagged, and the error was also much higher. So I can make a change over there and say make this as 50 and see. So these changes which I am making over there on the learning rate, that's the factor which is going to update my eta in my learning rule, and that does make a very important statement in terms of how fast it's going to learn and how fast it's going to converge. Although the major theoretical reasoning behind that is that this eta is going to scale down my gradients as being proportional to the weights which it needs to update. There are definitely some more questions which a lot of you can ask, which is that every single layer will have a weight of its own dynamic range, so eta should be different, and yes, that is also pretty much true. And that's what we do observe. So it's not necessary that always getting down a slower eta is going to make you a better convergent, or even getting down a bigger eta is going to give you. So if I change that even to 500 or 5000, maybe it does not come like this, but it starts jittering over there, and they are some of the interesting stuff you can play around with your learning rates. So down the future lectures we would be getting more of a clearer understanding into how this happens, and then why this happens in more of a way. So till then, keep on enjoying with more of these lectures, and do keep on coding as we continue with the theoretical lectures as well. And so then we see you for the next class.